Hello again, guys. Okay, so today I'm going to be solving this problem for you and explaining you how to do it. Let's first read the problem. It says the homogeneous beams AB, and CD weigh 600 pounds for this one and 500 pounds for this one respectively. Draw the shear force and bending moment diagrams for the beams AB and CD. That's what we have to do. For both beams, we're going to draw shear and moment diagrams. The first thing that we have to do is kind of imagining what is happening here and how we are going to be solving this problem. There are different ways. I can start and considering that everything here is connected, and I have this load here, and this is a fixed support, and I have three reactions in these fixed supports, 1, 2, 3, axial, shear, and moment. Or I can just separate both beams and start working first with this beam and then with this beam. This is the approach that I'm going to be using. Before doing that, once again, let's check something that I think is really important, that it says homogeneous beams. And it says the weight of each one of the beams. This is given to you for the reason of telling you that you have a distributed loading on this beam and you have a distributed loading on that beam. And the value of that distributed loading is, if you are working or you are talking about the beam AB, because it's homogeneous, I can get the total weight, which is 600 pounds, and divide that by the length, which is 6 feet. And the weight that I'm getting is 100 pounds per foot for AB. And I do the same thing for CD, which is 500 pounds divided by 5 foot. And then you have 100 pounds per foot. In other words, what we have in reality is this. We have distributed loadings here and here. And the values for those distributed loadings are 100 pounds per foot. Pounds per foot. Okay, once that we know that, then we can start solving our problem. I'm going to change this pen. I don't know if you can read that. Everything is too readable. So let me change this pen. I don't like it too much, but let's use it. Okay, first, I'm going to start with a free body diagram for the beam AB. And what you have in this beam is this. You have this situation, you have a distributed load here of 100 pounds per foot. We already say that. And we have a load of 200 pounds. This here is a roller. If it's a roller, it's going to be producing a load. Remember, this point is A, so this is going to be CY. And this, as you can see, is a pin. So it's basically, what I'm doing basically is doing a section and isolating this part. That's what we are doing here. So when you do that, then this is a pin, meaning we are going to have two reactions, By and Bx. And the distances are, this is 2, this is 2, and because the total is 6, that means that this is 4 feet. That's basically what we have over there. Okay. Now, If I want to calculate the reactions, I have 1, 2, and 3 unknowns. I can start by saying summation of forces in x equals 0, and then I get that Bx is 0. Perfect, done. And then I can say summation of moments in, and we knew it was 0 because there's no any other horizontal force here. And then I can do summation of moments anywhere, really. I'm gonna do it at C equals 0. So we do that summation of moments at C equals 0. Then we have 200 times 4, and it's positive because it acts in the same way. And this, remember, this is the distributed loading, and the total load is 100 times 6, which is 600 pounds. And the location is at the center of that distributed load, which is basically, if I do it with respect to this part here, this is going to be 1 meter, and this is going to be 3 meters, because that's exactly what is going to give me the center, 3 and 3 for that beam. So then you say 200 times 4, and then you say 600 times 1, which is the same one here. And then you have this other one, which is also By times 2, and it's positive. Positive because it's acting in the same direction and equal to 0. When you solve for this, then you say that By is equal to negative 700 pounds, or By is equal to 700 pounds acting opposite to whatever I assumed before. Immediately, remember, change and correct the direction for By. This is the value for By, 700 pounds acting in that direction. Now we can do summation of forces in Y equals 0. And if we do summation of forces in Y equals 0, then we have negative 200, negative 600, plus Cy minus 700 equals 0. And that will give you that Cy is equal to 1500 pounds. Done. First part, ready. We calculated these reactions. That means that we can start working with our beam. I'm going to copy now a scheme, a diagram just for that beam. So this is what we have. We have a load of 200 here. This is the roller, which we calculated a force reaction of 1500 pounds in that direction. And we have the other reaction, remember, is coming in this way. That's why I'm putting it like that, 700. And we have the distributed load acting here. The value for that is 100 pounds per foot, as we calculated before. And we include all of our distances for this problem. So this is 4, and this is 2. We can solve this problem by any of the methods that we studied before, but just for demonstration purposes for this particular problem, I'm going to solve the first part by sections. So I'm going to use the method of the sections to show how to do this. And after the method of the sections, I'm going to always also show it by the method of the areas as a way of checking my work, or also as a way of you learning the method of the areas. Okay, so let's do the method of the sections. Remember, if we're going to build a diagram, we have to draw a vertical line here at the beginning, at the end, at any intermediate support, wherever loads begin, wherever loads end, wherever I have a concentrated load, wherever I have a concentrated moment. In this case, it's pretty simple. I'm going to copy here my shear in pounds. I'm going to copy here my moment in pounds per foot, and this is the way we're going to start. So if we want to do that by the method of the sections, remember this is the point A, this is the point C, and this is the point B. We have to do first a section here in this part. So I'm going to work in the section A, C prime, if I call this point C prime, and you draw everything that is in that part. So you have 200 pounds, which is this load here, and you call this distance X. This is the distributed load of 100 pounds per foot. And remember, for this to be in equilibrium, at the end, at this end, you have to have a shear, you have to have a moment, and these are the positive directions of the shear and moment, and you should have also an axial force. But as we calculated before, there's no axial force here because there's no any horizontal force or axial force, better say, in this particular case. Okay, this force, this distributed load here of 100 is going to provide a force of 100 times x located at the center of the distance, meaning this distance is going to be x divided by 2. Now, once we have that, we can start basically and do our work. We can say summation of forces in y equals 0, and summation of forces, remember this is A, this is C prime, and here in this particular case I'm going to variate my x from 0 to 4, or if you want to see it in this way, from A, the position A, up to the position C, but just before the point C, right here, before touching that support. Summation of forces in y equals 0, so you have negative 200, negative 100x, negative v equals 0, or v equal negative 100x, negative 100x, negative 200. This is your equation for the shear. And then you do the evaluation. You're going to evaluate for v equals 0 and for v equal 4, which is the total length of the span. So for v of 0, if you put 0 here, you have 100 times 0 is 0 minus 200. So v of 0 is negative 200 pounds. And if you use the other distance, which is 4, for 4, then you're going to have negative 100 times 4, negative 200. And this is 400 and 200, so v of 4 is going to be equal to negative 600 pounds. Those are the two values that we are going to plot in our diagram. V of 0, I plotted at 0 here, is negative 200. That means that it's going to jump from 0 to negative 200. And the other value at 4, which is this other end, is going to be negative 600. Now, how to join these points is told you that answer is provided by this equation here. This is the equation of a straight line. That means that I'm going to join these points with a straight line. And now we do summation of moments. We're going to do summation of moments at C prime equals 0. You can do it anywhere, but at C prime I like to do it there. That means that then if I do moment here, I'm going to have 200 times x. That is positive. 100x is positive also. 100x is the force times the distance. We said that it was x divided by 2 minus m, no, plus m in the same direction, equals 0. So our moment equation is going to be 100 divided by 2 is 50, 50x squared, pass it to the other side, negative 50x squared, 200x, pass it to the other side, negative 200x. And with this, you can say that your moment for 0 x equals 0 is going to be 0, which makes sense because you don't have any concentrated moment at this point, so it should start in 0. And if you say for x equals 4, which is that distance, you can calculate m of 4, which is negative 50 times 4 squared, negative 200 times 4, and that gives you a moment for x equals 4 of negative 1600 pounds per foot. And those are the two values that we have. This value here is going to be negative 1600 pounds per foot. Once again, whatever shape is going to have this part of the moment diagram is given by the shape of this equation. And this equation, as you can see, is a parabola. Now, you always talk about frowny face or a smiley face. Well, yes, when the coefficient of the x squared is negative, then you are talking about the frowny face, like that, and it's a parabola, meaning these 2 points have to be joined by a parabola opening like that. There you go. And we have those points. Now, next step, we go and we do a section here in this other part. What is that part? That part is the span CB prime. So I can say that this is my span CB prime. And then once again we copy everything that is in that part. At least the way I'm showing you is this. There's a shorter, more complicated way of looking at it, but I don't want to tell you right now what is that way. And it's not that shorter, it's just a little bit shorter. This is 1500, and this distance is going to be x, because now my point B should be somewhere here, and this is the point B prime that I'm calling. This is C, and this is A. This load is 100 pounds per foot, and the distance here is 4. So once again, then we are going to do summation of forces in y equals 0. So if we do summation of forces in y, I'm going to pass this to the other side on a sheet of paper. So if I say summation of forces in y equals 0, then you have negative 200. Now, you can put this whole thing as one force, but I'm gonna divide it in 2 parts. One here, which is 400, meaning 4 times 100, and another one here, which is 100 times x for the forces. I'm gonna mark the distances. This distance here is half of the base, that means this is 2, and the distance from here to here also is going to be half of the distance, which is x divided by 2. Remember, we didn't put those values here, but at the end, always we're going to have shear, moment, and axial in case that we have the axial. So once we do that summation of forces, you have negative 200, which is this, negative 400, which is that. Then you have positive 1500, and then you have negative 100x, and then you have negative b equals 0. 600, this is 900. Negative 600 plus 1500 is 900, and this is negative 100, so my b is going to be equal to 900 minus 100x. That's going to be the equation for the shear in this span. What do we do then? Well, we say for x equals 0, my v is going to be 900 pounds. And for x equal, the new distance is 2, because this span, I didn't say it here, but remember, now we are talking between C, the x is governed by C and B, so my x is going to change from 0 to 2, which is the length of this span here. So x equal to, then I have my shear is going to be 900 minus 100 times 2, or 700 pounds. V of 2 equals 700 pounds. Okay, what means equal 0? Equal 0 means at this level. So at this level, my V is going to change from negative 600, which is the value that I had just before touching that point, to 900, which is the value that I calculated now, and this is going to be a jump here. Now, if you just analyze this jump, look, this was negative 600, and I found a reaction here concentrated pointing up of 1500. Negative 600 plus 1500 is going to give you this value, which is 900. But I'm just showing you how to do it by each one of the methods independently. And at the end, it's going to be 700, which is going to be this point here. And this equation, once again, is the equation of a straight line with negative slope, which is going to be that. And then you go to, finally, you go to the point B, and at the point B, you find this force of 700 going down, and you have a value of 700 here. So basically what you have is 700, and then you find this other force of 700, which is negative, and this is going to be 0. That means that you are closing in 0, and then you say yes. Yes, we did it. At least that part is correct, or that part might be correct so far. Okay, so now we're going to do the moment in the same span. Summation of moments. Moments where? Well, I'm going to do summation of moments at B prime, which is this point, equals 0. So then we said 200 times the distance from here to here. And that distance is 4 and x. 4 plus x. And it's positive because it's rotating in this direction. Now this 400 plus also times the distance from here to here, and that distance is 2 plus x. Remember, we are here. Now 1500 times x, but this time is rotating in the negative direction. And now we have this 100x force. Remember, this is the force. We have 100x force, and it's positive because it's rotating like that, multiplied by the distance from here to here, which is x divided by 2. We said it before, plus m equals 0. And then we solve. 200 times 4 is 800. 200 times x is 200x. 800. 400x. Negative 1500x plus 100 divided by 2 is 50, x squared, plus m equals 0. 800 is 1600. Positive, pass it to the other side, it's going to be negative, so moment is going to be equal to negative 1600. This 50x squared is going to pass to the other side also, negative 50x squared. And then we have negative 1500x, and then I have here 200x, 400x is 600, negative 1500 is going to be negative 900, pass it to the other side, it's going to be positive. And then you have your equation for the moment in that span. Same thing, you say for x equals 0, m of 0 is, this is 0, this is 0, negative 1600. That means that at this point we're going to have 1600, which it makes completely sense because this is a roller. There's no concentrated moment at that point, so we shouldn't have any change in this part. So that makes sense. And for x equal 2, the length of the span, then the moment is going to be equal to negative 50 times 2 squared, moment of 2, plus 900 times 2, negative 1600, moment of 2 is going to be equal to, this is negative 400, and this is negative 400 here. No, this is 4 times 50 is negative 200 here, and negative 1600 is negative 1800, positive 1800, 0. 0. That means that at this point, the moment is 0. And this equation is a parabola, first of all, and it's negative. Negative means that the shape is going to be a frowny face. Frowny face. This is the face of the parabola. Because the sign is negative, meaning this point is going to come and it's going to close in 0 like that. And now you can properly say yes, because you solve both of them, and both of them close in 0. There you go. This is the first part of the problem. This is the beam AB solved by the method of the sections. Now, let's go and let's continue. Now let's do the same problem just for showing the same part, the same beam, but using the method of the areas. I'm going to copy the beam again. This is the beam, 200. The only thing that I'm not doing now is calculating the reactions because we already did before. £1 per foot, distributed load, downward, distances, 4 feet, 2 feet. Vertical line at the beginning, vertical line at the end. Every time that we have an internal support where a load begins, where a load ends, when you have a concentrated moment, where you have a concentrated load. Here we are going to plot this is our 0 for our shear and for our moment in pounds and in pounds per foot. And then we start for the method of the areas. And then we say, okay, point A, I'm going to start with shear by the method of the areas. Shear. So you come to the point A. Remember, this is point A, this is point C, and this is point B. So you go to the point A and then you ask yourself the following question. Do I have any concentrated shear force at the point A? Well, the answer is obviously yes, because you have it here. It's a vertical force, which in this case is shear because the surface is horizontal, so it's perpendicular to our beam. This is a shear force of 200 and it's pointing down. That means that exactly at that point, my shear has to jump 200. So what you're going to do is concentrated load, jump, down. Why down? Because the load is coming down of 200. So my value in my diagram is going to be negative 200 from here to here. And I want you to explain something like that when you solve it if you use the method of the areas, just to be sure that you are solving it and I have something to grade. Now we go to the span AC. Remember, this is point, span, point, span, point. Now I go AC. AC. Well, I start with this value, negative 200, and then I find this area on top of that. That area is negative because the arrows are coming in that direction. Remember, that's why it's negative. And the area is 4 and the height here is 100. So negative 200 and this is negative 400. negative, no. I mean, the area is 400, and I'm applying the sign here. So the total value is going to be negative 600 pounds there. That means that at this point, this is going to be negative 600. Now, how I'm going to connect these 2 points? Well, when this shape comes from a constant area like this, it's going to be a straight line. So then you copy here, comes from rectangle, straight line. That's just for justifying that you are putting a straight line here. Straight line. Now we go to the point C. And at the point C, you ask yourself that question: do I have any concentrated load pointing in any direction but apply at that point C? And the answer is yes, we have a concentrated load at C. That means that this value, look at this value, at C, I have a negative value. If this is C, I have a negative value of 600 here, and I found a force of 1500 up. That means that it's going to be jump, concentrated force, jump up in this case, because the force is pointing up, and 1500 minus 600, I'm sorry, is going to be 900 pounds. And this is going to be the jump. And now we go to the span CB. And then you start from your 900s that you have here from the diagram, and then you find this area, and this area is a negative area because, remember, it's negative because of this, and this is 2, and this is 100, and then you say negative minus 200, that's going to be equal 700 pounds. 700 pounds, that means we're going to be here, this is going to be 700 pounds, and then you say, okay, 700 pounds, and how do I join these 2 points? Comes from rectangle, straight line. You join those 2 points with a straight line. And you go to the point now B, and at the point B you have a value of, this is the point B, you have a value here of 700 positive, and you find a force of 700 pointing it down. 700 minus 700 equals 0. You can write again concentrated force, jump down to 0. And then this is going to be 0, and then you say yes. First part done. Now compare these versus these calculations. Moment. Let's do the moment by areas. Well, if we do the moment by areas, then I have to start from my point A. Always point, span, point, span, point, span. So we start at the point A, and we say, do I have any concentrated moment at A? Do I have any concentrated moment at A? Look, do you have any here? No, you just have a concentrated force, not the moment, so that starts in 0. Now if you have a fixed support, for example, here, or you have an applied concentrated moment, then this shouldn't start from 0. But this is not the case. So that's 0 for beginning. Now we go to AC. And in AC, what I have is this part. So basically I'm going to start from 0, and then I have this negative area, which is just this area here. And this value is 200, and this value is 600. You see, 200 and 600, and this distance is 4. Well, this area, you can calculate it as, this is a trapezoid, or a trapezoid, so you have 600 plus 200 multiplied by 4, base 1, base 2, height, divided by 2, and remember it's negative. So this is going to be 4 divided by 2, and 4 divided by 2 is 2, 2 times 8 is 1600, negative. That's the value of the moment. So at this point it's going to be negative 1600. How do we connect those 2 points? Well, then we go to the circle. And the circle is, please don't neglect infants, neglect dumb people instead. Now, if this is the circle, first of all, this area is this area, and that area is negative. Why is negative? Because it's plotted below the axis, so it has to be negative. So the first letter is negative. Second, the area itself, I'm not talking about now the sign, but the area, this height is growing, is increasing as I go from left to right. That means that it's increasing. So negative increasing corresponds to this line, this part. And this is the part that is telling me that I'm going to join these 2 points using that part. Of course, this is a cubic equation. No, yeah, it's a cubic equation, not the parabolic. No, this is not a cubic, this is a parabola. But even if it was a cubic equation, you could do that because it's an approximate shape. Okay, now we go to the point C. Point C. Do you have any concentrated moment applied at C? No. No concentrated moment. No change. And now you go to CB. And in CB you find a negative moment of 1600 and a positive area. That positive area is 900, 700, 2, meaning negative 1600 plus base 1, base 2, multiplied by the height, divided by 2, and this is 0. So you close here in 0, which is good, but we don't say yes yet. And then we study the area. This area we said is positive, right? And it's going to be positive, and then the height is decreasing of the shape. So it's positive decreasing. Positive decreasing is going to be this part, which means we are going to join this in this way, and now we are going to say yes. And this is the method of the areas for solving this beam. So we already covered the method of the sections and the method of the areas for the first part of the problem. Now, this is just the first part of the problem. We have to continue now. Now, let's go to the second part of the problem, because I don't know if at this moment, at this time, you still remember what we have to do. But what we have to do is this. There is my problem here. This is the problem. We work with this part. Now we have to work with this other part, which means that somehow I have to transfer whatever I have from my loads from the other part. So let's do that. I'm going to copy once again the original problem, and the original problem that we have is this. This is the beam A, CB, and in this beam you have the 200 load here, and we calculated the reaction of 1500 and a reaction of 700. But if you remember, this is connected by a roller and by a pin to the other beam, which is here. and it has, well, this has the distributed load also, and this part has also a distributed load that we calculated of 100 pounds per foot. But these loads, for action reaction, if at this end is applied like that, at the other end has to be applied like that. Same value, and if this is applied like that, at this end, it has to come like that, action reaction, 700. And this is the beam that I have to solve. Now, if you study just this beam, now, this is a fixed support, and in that fixed support, we have dx, dy, and a moment, md. Why d? Well, because this is A, B, C, and this is the point D. And the distances from here to here are 2 and 3 feet. These reactions, I don't really need to calculate them in order to do my shear and moment diagram. If I'm in a rush, if I'm in really rush, I don't have to calculate this reaction, because remember, I'm going to start plotting it from here, and once I reach the other end, these are going to be the values that I need to make it go to 0. So be smart if you are in a rush. But we're going to calculate them for demonstration and for checking also my results at the end. Because if I don't know these values, I don't know if it's going to close in 0 or not. But if I know these values, yes, I can know if it closes in 0. So let's start with summation of forces in x equals 0. And the only thing that we have is dx, which we knew it was going to be 0. And then you do summation of forces in y equals 0. Wait a second, summation of forces in y. He's always yelling at us that we do summation of forces in x and y. Yes, I always tell you that, but in this case, the only unknown that I have is dy, so I can't do summation of forces in y. So if we do summation of forces in y, we have this force, which is negative 1500, which plus this force, which is positive 700. And now remember that the vertical load, distributed load, is going to produce a vertical load here, and that value is going to be 5 times 100, or 500 pounds. And the location from this point is going to be 2.5, because it's the center of that beam. So this is going to be then this force, negative 500 plus dy equals 0. This is 2000, this is 1300 negative, pass it to the other side, dy is 1300 pounds to the other side. And now we do summation of moments wherever you want to. I'm going to do it at D. So if I do summation of moments at D equals 0, and only in this part, remember I could have done it from the beginning and do moment here and calculate directly the moment with the whole beam connected, and I don't consider these forces, these intermediate forces, because they are connected. But we did it by parts. So summation of moments at D equals 0 only in this part. If it's only in this part, then I have 1500 times 5, and it's acting in this way. If this somehow confuses you, draw it again, put it like that, because that's what we're having there, this, like that. So 1500 times 5, then I have this 700 times 3, and it's going to be in this direction, negative. Then I have this force, and that force I calculated before as 500, and it's going to be positive 500 times 2.5. And then I have this moment that I assume it in this direction. And when you solve these, you solve for MD, and MD is 6,650 pounds per foot. And those are our reactions for that part. Now we can start creating our shear and moment diagram for that beam, which is called the beam CD. Remember, this point is B here. So let's do that diagram. let's copy only that beam now, because I'm going to do only the diagram for that beam. We have the reaction of the roller, 1500. We have the reaction of the pin, 700, and we have dy. I calculated dy and it was 1300, and we have the moment at D, 6,650 pounds per foot. Distances, I know I mess up the scale. This is 2 feet, this is 3 feet, but the distances are there. So, and we have the distributed load acting here, and the value is 100 pounds per foot. And this, for this part, I'm gonna solve it by the method of the integrals, just for showing methods, not because I have to do it by any particular one. Vertical line, vertical line, vertical line. This point is C, this point is B, this point is D. Horizontal line for my shear, which is going to be in pounds. Horizontal line for my moment, pounds, foot. And then we start. And we start at the point C for the shear. Do I have a concentrated load at C? And the answer is yes. You go to C and you find a concentrated load of 1500 acting downwards, which is going to produce a jump here downwards, and this is going to be negative 1500. From now on, we apply our method of the integrals, and we go to CV. Remember, the shear is the integral of the load, dx, plus this coefficient that I'm calling CV. And CV is the value of the shear at the beginning, meaning at C, directly read from the diagram. That means that I'm going to read it from my diagram, from there. And this is the value of CV that I set. Now, I already have this value now, is negative 1500. Now, what is the value of the load here? Well, the load will be equivalent of having this line. And this height here is 100. So if this is X and this is Y or W, then the equation of that line is going to be W equal 100. So my shear is going to be the integral of 100 minus 100 dx minus 1500. 1500 is this, and this is 100 plus dx. Now pay attention, because this is correct, but the loads are coming down. Because these loads are coming down, that implies that this integral has to have this negative sign here, only for the shear and only for the integral part. And that's one of the most common errors. People forget about that. So my shear is going to be negative 100x negative 1500. That's my equation for shear. I'm going to put it A in case I need to call it somewhere again. And then you do the evaluation between the span that you are analyzing, because you are here between 0 and 2. So if you say V of 0, you put 0 here, this is going to be negative 1500 pounds. And if you say 2, and if you say now x of 2, so if I have to calculate 2 at the end of this span, then this is going to be negative 100 times 2, negative 1500. And this is going to be V of 2 equal negative 1700 pounds. Box your answers, put your units, That means at here now is going to be negative 1700. This is a straight line. X, this is going to be a straight line. If I want to calculate how much is the shear for x equals 0.5, I just put here 0.5, and then I measure this value here at x equals 0.5. Now, instead of continuing, or let's finish the shear and then I'm going to go back to the moment. Let's do it like that better. Now you go to the point B. Point B, do I have, let me put it here, question. Then I ask my question. Do I have any concentrated force acting here? And the answer is yes, you have it. So you have negative 1700. And then you find this force exactly at that point, pointing up, of 700. That means that it's going to jump up from here to here. And that point is negative 1000 pounds. And now we move to BD. And then we said, okay, we said shear is the integral of W plus CV, and that CV is the value of the shear at the beginning of the interval, meaning in this case is at B. Once again, read from diagram. Read from diagram, meaning I'm going to read it from here. This is my CV for this part. Read from the diagram, right there. And the load is the same case, like this. So my V is going to be negative 100x, only because it's the same load, but the constant is changing. Now it's 1000. You can do the integral, etc., etc., etc. Okay. And this is the equation. Now what do you do now? You do for x equals 0, then you do V of 0, and this is negative 1000 pounds, which is this value, and we already calculated before, right? And for x equal the distance, which is 3, V of 3 is going to be negative 300, negative 1000 is negative 1300 pounds. That means that from this point we're going to reach this value here, which is negative 1300. Actually, it should be above there. And this is a straight line, so that means this value is going to be a straight line here. I'm going to put here equation B just in case. And now the last part is going to the point D. Point D. Negative 1300 is the value there. And you find a force of 1300 going up. Then make it 0. And you say, yes, go to 0. That's the first part. Done. Now let's go with the moment. And for doing the moment, we start again. Moment. We start at the point C. Question. Do I have any moment? No moment. 0. That means that your diagram starts from 0. And then you go to CB. You say moment is the integral of the shear plus Cm. And this Cm is the value of moment at C in this particular case, which is the beginning from the diagram. That means that this value here is going to be your Cm for the first span, because it's at the beginning read from the diagram, so that is 0. What is your V? Well, the V is the equation A that I called before. So my moment is going to be the integral of the shear, but the shear is this value here. So it's going to be the integral of negative 100x, negative 1500 dx. And notice that I don't put any other negative sign anymore, because that negative sign was included in the shear and it's taken care with this. So the moment is going to be equal to negative 50x squared negative 1500x. For x equals 0, moment is 0. For x equals 2, this is negative 50 times 2 squared, negative 1500 times 2, 200, 1700, right? This is 4, 200, no, 200, 300, 3200. Pounds per foot. Negative 3200 pounds per foot. This is a parabola, and it's frowny parabola because of the negative of the coefficient is giving you this, meaning this is going to be that. Now you go to the point. Point what? Point B. And you say point B, no concentrated moment, because there's no moment applied there. No change, no sudden change, no jump, no nothing. That makes sense, right? Now BD. BD, the moment is going to be the integral of the shear. But the shear is the shear of this span. And that shear is this shear that we calculated here before. So then the moment is going to be the integral of this, negative 100x, negative 1000. Let me put the equation here. Moment is the integral of V plus Cm. That Cm, remember, is the value of the moment at B, read from the diagram, meaning 3200. That's my Cm for this part. So the equation is going to be negative 50 x squared, negative 1000 x, negative 3200. And then you say for x equals 0, just for verification purposes, I'm here, this is 0, negative 3200, which is correct. And for x equal now 3, moment for x equal 3 is negative 50 times 3 squared, negative 1000 times 3, negative 3200, and moment for 3 is negative 6650 feet pound. So that means that from this point it's going to jump up to negative 6650. And once again, this is a frowny parabola, meaning this is from here, it's going to come frowny up to this point, like that. And now finally, we go to the point D. And please pay attention, because this is new. I didn't explain this before. I haven't explained this before. So now we go at point D. And at point D, we ask the question, do I have a concentrated moment at D? The answer is yes, we have it. And I have a concentrated moment at D like that. Okay, this is a new I'm not gonna say rule, but if we are using this type of plot for the shear moment diagram, you have to do it in this way. So every time that you see a concentrated moment in the diagram, if the moment is like that, counterclockwise, concentrated moment is like that, you're gonna consider it positive for this. And if the moment is clockwise, you're gonna consider it negative for the diagram, no matter what. So then, do I have any concentrated moment at D? Yes. I start with this value, which is negative 6,650, and then I find this moment from the diagram that I calculated before, which is like that, and is 6,650, and this is gonna be giving me 0, meaning this is gonna be jumped from here to 0, and now you say your big yes because you deserve it. You see, that's the new part, basically. Well, this problem has two new things. Not new, but one of them is that we have to separate the beams in parts in order to solve each one of the parts, but the second part is this one. And every time that you have a concentrated moment in the beam, the way you're going to show it in the diagram is whatever is counterclockwise is going to be a positive jump, and whatever is clockwise is going to be a positive jump. Clockwise is negative jump. For concentrated moment, this convention. Learn this, please. Now, if you want to, we just can solve this for the method of the areas also, or verify it at least for you to do it. But we can do it really quick for the method of the areas, because the method of the area is really quick to do. The same part. So this is what we have. 1300, 6650, 700, and 1500 here. And then you have these, and then you have that. Member shear, pound, and moment, pound per foot. Distributed load of 100 pounds per foot, and this is 2 feet and 3 feet. So we start once again point C. Point C. What do you have in the point C? It will help if I know what the point C is, right? This is the point C. Then you ask yourself the question, do you have a concentrated load at point C? Yes, I do have a concentrated load. I have a concentrated load of 1500. That means that jump down in the diagram. So from here, it's going to jump down to 1500. Negative, of course, because it starts from 0. Now, the span CB. For the span CB, you have negative 1500, and this is a negative area also, and the negative area is 2, and the height is 100. So negative 1500, negative 200 is negative 1700. That means that you're going to be here. And because this is a rectangle, because comes from rectangle, straight line. I'm not writing this just because I like to write stuff, guys. I'm writing this because I want you to do the same thing in the test in case that you're using this. So this is a straight line here, 1700. Now you go to the point B. You have negative 1700. You ask the question, do I have a concentrated load? Yes, I have a concentrated load of 700 pointing up. So that's negative 1000, meaning this is going to come here to negative 1000, jump up. And then you go to BD. And in BD, you find this value, negative 1000, plus this area, which is a negative area. That's why I put negative. Why is negative? Because the arrows are pointing downwards, and this is 3, and this is 100. So this is 300 negative, 1000 negative, negative 1300, meaning this is going to come here to negative 1300. Because comes from rectangle, that means that is straight line. So these two straight line, and then you go to the point D. Point D, I have negative 1300. Oh my God. Negative 1300, and I find a positive force pointing up of 1300, and that is 0, and then you say yes. And then we do the moment part. For the moment, we start at the point C. Point C. Do you see any concentrated moment? No, right? So no concentrated moment. 0. So that means that starts in 0. Now go C, B. Is 0 plus this 0 plus this area. That's a negative area, and this is 1500 here, and this is 1700 here, you see? And this distance is 2, so it's going to be 0 minus 1500 plus 1700 multiplied by 2 divided by 2, which is negative 3200. So you're going to reach this point, and this point is negative 3200. This area, please don't neglect infants, neglect dumb people instead. This is negative, negative. The height here or the height here is increasing, so it's negative increasing. Negative increasing is this. Negative increasing is that. That's what I'm going to do. Negative increasing. Point B. No concentrated moment, no change in the moment in the diagram, no jump. And now we go BD. And BD, you have negative 3200, and then you have this negative area. This negative area looks like that. 1300 here, 1000 here. Negative 1000. Negative 1000 this end, negative 1300 this end, and this distance is 3, and it's negative, remember, so it's going to be negative 3200 that comes from the diagram minus this area, and this area is 1000 plus 1300 times 3 divided by 2, and this is negative 6650 pounds-foot. So that means that we're going to be going up to negative 6,650 this point. Once again, please don't neglect infants, neglect dumb people instead. First is negative because the area, this area, is negative. And then, once again, it's increasing, right? Because this height is getting bigger. So it's negative increasing, and it's going to be this part from here. I go up to that point. This is going to be the point. And now the last part. The last part is that at the point D, we found a force. Well, first I have negative 6,650. But then I find this concentrated moment. And the concentrated moment is acting in this direction. That means that it's positive. Remember, once again, I'm going to write it again. For concentrated moment, positive. For concentrated moment, negative. This is positive. This, negative. Plus this, positive is 0. That means this jumps to 0, and you say yes. Okay. You remember, I hope that you remember at the beginning when I started solving this problem that I said, not exactly at the beginning, at the middle of the solution, I was doing, let me see what part I was doing. I was doing this part. And then I say, okay, you know something? It's not, even though, you know, this is what is happening here, and I have these two forces and these two parts and these two beams, and I calculate one beam, and then the other beam is connected to it. Actually, this is the one that we were using. So we said this part here and this part here, and then I work first with this one, and then I have to come with this one, and these are the reactions here. And I say, well, in reality, I don't have to calculate those reactions. Not in reality, I don't have to calculate those reactions because I start from this end. And that's what we did. Look, when we started from this end, we start everything from this end, and I didn't need those reactions until I reached the very end of the beam. So if I reach this point and I didn't have the reaction, once I'm at this point, I know that if the problem is correct, the only possibility, even if I don't have these numbers, the only possibility for this to close in 0, if I am here at negative 1300, is to find a positive reaction pointing up. It's the only possibility. So that's the value of the reaction. Same thing here. If I'm a negative moment here, the only possibility for closing in 0 is to find in the beam a positive moment, which in this case is counterclockwise, acting on the beam, and that was the value of the reaction. So it doesn't hurt calculating the reactions. Actually, it helps a lot because it tells you if what you're doing is correct or not. But if you are in a rush and you don't have time to calculate those reactions, at least in that particular case, when you start plotting from the other end of the reactions, then start doing it and don't calculate the reactions. But usually I hope that you have time because you are practicing a lot. Okay guys, I hope that you enjoy. This is actually not a long problem. The problem is really short. The thing is that we did it like 3 times every part with different methods. Remember, we cover sections, we cover areas, and we cover integrals for this particular problem. See you in the next video. I hope that you enjoy it. Study.